Okay, so let's go over a couple of examples. In some cases I provide a solution only, in some other cases I provide the equation where it comes from. But in most of these examples, in all of them actually, you should be able to answer the question just by looking at the solution. So take your time to write down these examples, or you can pause and write each example as I go over it. So, to put the framework for the whole part here, each of these examples is the solution of a motion in a mass spring system. So let's assume what you see here basically comes from a mass spring system. So again, you can have various questions based on just the equation and the solution given to you. So let's go over a couple of these examples or questions. Just by looking at this, if I ask, okay, what's the mass of the object? You go in immediately and say, okay, it's 1, because that's the coefficient of y double prime. What is the damping coefficient? That's 2. As long as you have y prime there, that means that there is damping in the system, so that means b equals 2. Then I look at the solution, which you can determine, or you can use Maple to find it. You can check for yourself at least the homogeneous part of the solution. How do I recognize the transient solution or the steady state solution? Transient solution is the part that goes to 0. Remember, if there is damping in the system, there has to be an exponential which is negative. So that is what causes that part to go to 0. So transient solution is another name for the homogeneous part of the solution, and it's recognized in the mass spring system by the presence of the negative exponentials. Is it underdamped, critically damped, overdamped? Well, I have complex roots. I can actually tell what those roots are. -1, that's alpha, plus minus 2i, 2 is beta. So we are in the complex case. Obviously, this is an underdamped system. And of course, once this goes to 0, what's left is the forced response, or the steady state solution. Is the part that basically remains after you let the limit go to infinity for t. What about the second example? Well, immediately you notice there is no damping in the system. There is no y prime, b equals 0. There is no damping. What about whether the system is in resonance or not? Well, resonance means when the frequency of internal motion of the mass spring system is equal to the frequency of the external input, of the forcing term. If you look at the solution here, the frequency of the mass spring system is 2, the coefficient of t, and the frequency of the forcing term is 1. So the frequency of the forcing term is 1. They're not equal to each other. The system is not in resonance. Okay, so that means the motion is fully periodic. There is amplitudes, but they don't go without bound. So there is bounded oscillations, and again, because the frequencies are not equal to each other, and again, this whole resonance versus no resonance case is only when you have no damping. As long as you have damping, there is no issue with the duplication. So if there is damping, some portion goes to 0, and then there is going to be a steady state solution. Now mirror this example 2 with the example 3. All I did here, I essentially changed the frequency of the external force, which is now 2. So the frequencies match. So this system is in resonance. We have unbounded oscillations. And of course, the unbounded oscillations are also revealed by the external t. That as t goes to infinity, that's the part that causes the oscillations to go without bound. So once again, how do I recognize resonance? Nothing goes to 0. There's no negative exponential. And then the frequencies match. And there's the extra t. They always come hand in hand, right? I mean, if the frequencies didn't match, there wouldn't be any extra t, because you don't have any duplication in that case. What about example 4? Critically damped, overdamped, underdamped, undamped. Well, there is damping for sure, because we have negative exponentials. And you obviously are in the second case, critically damped, because you have a single root and the extra t here. So you have critically damped system, and once again, this portion here is the transient solution, the part that goes to 0. And then we can ask, of course, other questions, right? I mean, like if I give you the mass, find the spring, constant damping, and so on. I mean, yes, because you know where -3 comes from, right? I mean, you know that, let me see if I can actually put this here. You know that -3 actually is minus b over 2m, and you know that in the critically damped case, b squared minus 4mk is 0. So it's enough for me to give you one of these values, and you can have you can find the other 3. And since I just did that, why don't I actually just do this little exercise? Let's say I give you the damping is 3. If the damping is 3, what do I get here? Let's say there's going to be 3 equals 3 over 2m, and 2m is 1, m is equal to 1/2, and then you plug in b and m right here, and you can find b, right? So that means b squared equals 4 times m, which is 1/2, times k. Actually, b is known, right? So I can find k. So b is 3. So I have 9 on the left, 2k, and then k equals 9 over 2. Right? So b equals 3. If I give you that, that gives me m equals 1/2. And then you can plug it in here, b squared, which is 9, equals 4 times 1/2 times k, 2k, k 9 over 2. Yeah. So again, in the critical damped case, I can give you one value, and you can find the other 2 physical constants. So finally, one last question I want to focus on here. So in this example, notice that I didn't specify what omega is, the frequency of the external force. So basically, I didn't specify the external force. And let's say the question is, find the resonant frequency of the external force. So the resonant frequency for omega. All right. So in other words, what should be the frequency of the external force for the system to be in resonance? That's like a fancy question. Actually, it's a very straightforward one, right? Because you must remember, resonance happens when the frequencies are equal. Right? When the frequency internal to the motion of the mass spring system matches this omega. So all you got to do is to basically solve for the homogeneous part, and that gives you the frequency, right? Because that means r is equal to plus minus 3i, and you know that the homogeneous part of the solution, then it's combination of cosine of 3t c to sine of 3t, and the frequency then that matches the internal frequency of the object is 3, right? So to have resonance, omega must be equal to 3. This you may want to avoid, right? I mean, if you want to avoid resonance in the system, then it's important to know when that happens. So omega should not be 3 if you want to avoid the system to be in resonance. So if you want to avoid unbounded oscillations. So that's it for today. Last thing to do immediately after you go over this, go over the Camtasia demonstration to see how these examples look like on Maple, and take the time to run those examples yourselves. If you don't have Maple on your computer, you can access Maple remotely via the IT website. Thank you, and I'll see you later.